All right, so I'm Adam, and I did this work together with Patrick Johnson. And what I'm going to talk about is an Agda formalization of the transitive closure of block matrices. So let's check this out. So Jean-Philippe Bernardi and Patrick Johnson did some work on implementing Valiant's parsing algorithm in Agda, where they had an encoding of matrices and did interesting things with it. And this work is kind of structured in the same way as that, but with a more general matrix implementation. So I'll show you matrices in Agda, and this is an example of kind of how the structure of them look. And I'll finish with an implementation of the reflexive transitive closure of matrices. That kind of looks like this. So first, the matrices. So we want them to be easy to program with, and I want them to be easy to write proofs with. And in my case, this means that I rule out these kinds of things. I don't want to do like the vectors of vectors, where you kind of have to work through rows of rows and things like that. And I don't want to do function from indices, since I kind of want to do pattern matching, on my matrices. So we start with this kind of a way of describing the shape of the matrices. And some of you might recognize this from Jeremy's talk this morning, where he had exactly the same construction. So we have shapes of matrices. So we can have there we go, single things, or we can have branching things. And they're kind of a generalization of natural numbers, though I do not have a zero, but it's fine anyway for describing matrices, since I do not want empty ones. So small example of using this one is this row matrix, where we have a shape of branch of leaf, and a leaf at the end. And we get this block structure. And so let's look at the matrix. So we have a data type with a set or a type for the contents of the matrix, and then we have a shape for each dimension. So here, this is an illustration of the constructors of my matrix. So first we have the single element matrix, which can only contain some other value, right? And then I have a constructor for row matrices, and as we can see at the type here, this can only contain other row matrices, so there's no columns inside these small boxes. And the same with the column matrix, which is constrained to only have columns inside it as well. And then we have this quad construction, where we can have whatever you want inside. And let's have a look at the actual data type definition. So we have the one case, and we have the columns, where, as you see here, we only have columns inside the column matrix. And we have the row, where we only allow rows inside of it. And then we have the quad matrix, where you can see that the shapes of these two correspond, as they do here, and the number of rows correspond here as well, and there. So my development is structured using a bunch of Agda records. We start with a seminary ring with an equivalence relation, a plus, a multiplication, and a zero. And we have a couple of laws associated with this, that plus is associative and it commutes, and zero is the identity of plus and the zero multiplication, and that multiplication distributes over plus. And then I extend this to a semi-ring with the one, and that the one is an identity and that multiplication is associative. And then we get to the closure operation, which is an operation, I call it star. It's with this specification. So the star of something is 1 plus that something multiplied by the star of the same thing. This is an example of this star operation. Could be like in regular expressions, you have a star operation that kind of means exactly that. So what I did then was that I took my matrix thing and lifted element types into a matrix seminary. And we only do this for square things, so we only need to index over one shape when we lift it. So this was the main amount of work. All the proofs regarding the matrix structure, that they actually satisfy all the laws of my semi-ring, and closure. So here's a simple, the simplest part of it all, I'd say. So in the semi-ring we had an equivalence relation, so we have to lift it to the matrix structure. So the big S thing signifies that we do it on matrices instead of the small s, where we have on the elements. So we lift the single element to just be the equivalence on the elements, and on the rows it's a product of equivalences, and so forth. And then we need matrix multiplication, which is this is pretty nice, since it's kind of like textbook matrix multiplication. In the single element case, it's pretty easy, but in the row case, you get the row times the column. So row and from the column, and so on for all the cases of the matrix. So this is the end goal of the formalization. This definition of the transitive or the reflexive transitive closure, which is quite daunting, I'd say. So it's a inductive or it's an inductive definition. So we have the single element matrix, which is just use the underlying operation. And then we have the quad matrix, which leads to this horrible expression. So what I did was that this is just a function in Agda, right? So and it comes with this proof, which turns out to be so it turns out that this definition is actually correct. So I want to give an example of how you can actually use this. So here is a closed semi-ring of booleans. So we have the 0 is false, the 1 is true, plus is disjunction, and the multiplication is conjunction, and the closure of any boolean is true. So what I do with this one is that let's look at the graph, right? So we have a very simple graph, and we can translate it into its adjacency matrix. And then if we take the closure of this, we get the reachable nodes. And if we take a look at the definition of the closure, we can see that the 1 appears at the diagonal, and just the W appears, let's see, there, and then we have the squared W, which appears there. So in this case, it's not too hard to compute by hand or something, but in general, of course, it's much harder, and we don't, and it actually doesn't use this formula, right? So it used the one I showed you before. Okay, so I talked about Bernardo and Johnson, what they did. So if we want to do parsing with this matrix structure, we would have to invent or make a closure over the semi-ring instead of my work with the semi-ring. And the actual algorithm for computing the closure, we first found it in Dolan's Fun with Semi-rings. So we have matrices in Agda, and but I don't think this is perhaps the best way to do it. So I'd like to look at, maybe you can make it sparse, add a 0 matrix perhaps, or something like that. And you can experiment with removing constructors from the matrix, and you get different properties and possibly easier written algorithms, or in some cases harder. So, and something that I would think would be very interesting is to, if there's a nice kind of mapping from efficient storage, like row major storage, into my kind of block matrix structure. So that would be very, very cool if there was such a thing. And I think automation would be suitable for this kind of work, since a lot of the proofs are kind of, they're quite tedious, but they often boil down to induction over the matrix structure. And something we did not look at was the performance or the complexity of the closure algorithm. So we don't know if it's efficient or it just does what we want, right? And as I said, if you want to do parsing using the Valiant algorithm, we would have to generalize to the closed seminary. Okay, so if you want to have a look at the code, it's available online. And yeah, that's it from me.
For the performance of your closure algorithm?
Yes.
Like computing the closure is in some sense very similar to computing the inverse of the matrix. And often what is faster is to just solve AX equals B as a forgiven right-hand side.
Yeah.
And the same thing you can do for your closure if you only compute it for a specific. That's can be faster.
Okay.
You don't need that in general. But I'm not sure how you do it in Agda or something.
Might be a way to do it.
Then you have your different decompositions, LU and so on. It also translates to the closure.
Yeah, go ahead.
I mentioned there are many applications to this library. Have you found any particular one where the proofs are very relevant and change the day?
Sorry?
I imagine there are many applications. What's the most glorious one?
I have no idea what that could be. Yeah, I guess you can do quite a lot with this closure operation. You can this is just the simplest example, computing a reachability right. So there's limitless, I guess, opportunities for using it.
Yeah.
Here in the.
In your definition of a semi-theory, you have equivalence. Usually, in the definitions of where the semi-rings I've seen, it didn't have equivalence. Is that just taking the place of usual equals in the usual formulas I would see otherwise?
Yes. So in the Boolean seminary,
Yeah.
it's just propositional equality. This equivalence. But if you want something more advanced, you can do it.
Whatever equals relation.
Yeah.
So it looks to me as if, for a given shape of a matrix, you can have multiple ways of constructing it, right? And so, I mean, are some ways better than others?
So do you mean
Some
like?
kinds of algorithms, or have you looked at that or about that?
So when you say for one shape, you can have different.
So here you have a little box of 1 3, why you can have a box of just 1 and then a sub box of 316, right? I mean, there's more than one way to make something that ends up having the same, it's a matrix with the same
With this,
not the same shape.
yeah, the same. All right, yeah. So like this one, there's two
Yeah,
threes, right? Yeah.
And so some algorithms might be better on some constructions, and I mean, have you thought about that or looked at that, or?
I have not looked at it, but so I know if we want to do things in parallel, right? So then it benefits us to have a kind of balanced shape.
Okay.
Yeah. So we can do as much work as possible in parallel if the algorithm actually does work in parallel. But yeah, I guess you could. This is an interesting avenue of further exploration.
So I have a question. You have your shapes. You just have a singleton, and then you have a pair, right?
Yeah.
Do you think this might generalize to sort of the stuff that Jeremy was presenting this morning, where you can have sort of arbitrary Napierian functor shapes? How hard would that be, or do you think it would even work?
I don't know. I guess wouldn't be impossible to generalize this shape to something else. I don't know how it would look in this specific development, right?
Yeah, the question is, would the proofs of like the semi-ring lifting properties and things like that, would those still go through, or what properties would you need from your shape for those?
So the okay, so if we were to change this shape data type, we would have some since it's kind of closely connected with the type of actual matrices. So
Right.
I would have to change the matrix type to something else that accepts different kinds of things. So, which could be perhaps possible to do, since it's kind of with what constructor I use here is exact determined by the shape. So you could probably do some kind of computational type on it.
An interesting extension would be matrices with symmetry, so symmetric matrices, some property, zeros on the determinant, on the diagonal.
Yeah.
I was once looking at matrices in An Agda, now simple matrices, and the most challenging problem is actually associativity of matrix multiplication. If you try to do it by hand, you fail because actually you have to do it as in mathematics, where you say a matrix corresponds to linear functions, and it's just associativity of, and it's just associativity of function composition. Have you looked at something like this?
Sorry. So you did matrices as.
If you look at associativity of matrix multiplication, and you try to do it by hand, you fail completely, because actually the thing is how it's done always in mathematics, that you say matrices correspond to linear functions.
Okay, yeah, okay.
And you have composition of linear functions, and then it's trivial there, but you need to go back and forth. So if you look at something like this, for instance, like I think an obvious thing would be to look at translating the matrices into some kind of linear functions. It must be more complicated because you have the shapes.
Yeah. No, I haven't looked at it, but yeah.
I could just give a comment that the motivation for getting started with this work was to avoid the dots in all the math books, I mean, all the indices and so on. Say, okay, what if we only look at 2x2 matrices? And it seems that almost all operations and so work fine with just a quad constructor, and then you have to have something to not only get 2 to the power n times 2 to the power m. So you have to have something to make it uneven, like row, column, or a 0 and 1. But it's lots of nice things come out when you just look at that, because of course you can't do too many mistakes when you make a matrix multiplication with 2x2 matrices. So you sort of reduce that possibility, and then everything that recursively goes down. So that's like the nice idea, and then you just play it. determinant doesn't need to work.
Oh.
All right, let's thank our speaker again.